In section 4.3, we're going to continue talking about linear independence, and then we're going to combine the ideas of independence and a spanning set to introduce the concept of bases. So first, let's talk about linear independence as regards to a general vector space. So the definition is going to be very similar. In fact, it's the same definition as we had before, except that we're going to be talking about vectors in general in a vector space instead of just normal vectors in Rn. So a set of vectors in a vector space is said to be linearly independent if the vector equation c1v1 plus c2v2 all the way to cpvp is 0. Or I should say, if that linear combination is 0, then all of the ci's have to be 0. Only the trivial solution exists for that homogeneous equation. The set v1 to vp is said to be linearly dependent if there exist weights c1 to cp that are not all 0. And again, something is either linearly independent or dependent. This is the same definition as we had before, except now we're talking about general vectors, not just vectors in Rn. And the following results from when we introduce linear independence at first in chapter 1 still holds true. We have that a set containing the 0 vector is linearly dependent. A set of two vectors is linearly dependent if and only if one is a multiple of the other. And a set containing one non-zero vector is linearly independent. All these we got from section 1.7, and they still hold true for general vector spaces. So let's look at some examples. Example 1, we have these three vectors. These are given as matrices, but these might be vectors in M2 by 2. When we talk about all real 2 by 2 matrices. And note that this symbol, which we're going to see sometimes, this means in. That little E looking symbol. So these are three vectors in the vector space M2 by 2. And this is going to be a linearly, because we have the 0 vector in that set. And we said on the previous page, if the 0 vector is in that set, then it has to be linearly dependent. The next example, again, we have two vectors in M2 by 2. This is going to be a linearly independent set because we have two vectors, and if we have two vectors, it's going to be dependent if and only if one is a multiple of the other. And in this case, 3, 6, 9, 11 is not a multiple of 1, 2, 3, 4. We can check because each entry would have to be a constant multiple. So for instance, to get from 1 to 3, we would have to multiply by 3. And that also works for 2 to 6. But it's also going to have to work for 3 to 9. And 4 to 11. Which does not work. It is not multiplied by 3 to get there. So therefore, it's not a multiple, and therefore that set is linearly independent. Now a theorem that we could have introduced in chapter 1, as it holds true for any vector space, if we have an index set of vectors, index means that there's an order to those vectors, with v1 not being to 0, so it can't have the 0 vector, it is linearly dependent if and only if some vector vj, with j greater than 1, is a linear combination of the preceding vectors. And I think that this is maybe a little bit obtuse. How about instead we say that it is linearly dependent if and only if some vector can be written as a linear combination of the other vectors. As that's what we're really trying to say, we're just going to be putting an order to them and saying that we can order them and say just the preceding vectors we talk about. But if we know that we can write one of the vectors in the set as a linear combination of the other vectors, it doesn't necessarily have to be the last vector and then look at the preceding ones, then we have linear dependence. And we said something similar in chapter 1 to that regard. So let's take a look at that. We have another example of vectors. These time vectors are going to be polynomials. We have P2 here, and let's recall that P2 is the set of all polynomials of degree at most 2. So quadratic polynomials and below. And we have three vectors. These vectors are going to be t, t squared, and 4t plus t, 2t squared. And is this a linearly dependent set? Now, we don't have to go back to the definition. We have this theorem that we can use that since P3, 4t plus 2t squared, is 4 times P1 plus 2 times P2, right? P1 is t, and P2 is t squared. Since I can write one of the vectors as a linear combination of the other vectors, then this is a linearly dependent set. And note that we could have done a very similar thing in this first example with this linear dependent set. Using that theorem, we could say that 0, 0, 0, 0, the zero matrix, or zero vector in this case, is equal to a linear combination of those other two vectors by just using zeros to multiply them together. And that is why we can always have a linear dependent set if we have the zero vector in it, as you get a trivial linear combination of preceding vectors or other vectors in the vector space. And that is also why example 2 that you can rewrite, if you have two vectors, you can rewrite one as a multiple of the other. That is a linear combination of the other vector. So let's look at vectors in R3. We have this H is a plane illustrated below. So H is this plane right here in R3. And we're going to look at valid descriptions of H. We talked about that we can let H be a span of vectors. And now we're going to be thinking about that span and what kind of things represent this plane. So first off, we have H is the span of V1 and V2. And let's see if that's true. V2 is this vector right here. V1 right there. And since those two vectors are not multiples of each other, they are going to span the entire plane. Any point that you pick in this plane, so let's say this point right here, we can write this as 2V1 plus V2. If we go over twice in the V1 direction and then once in the V2 direction, we can get to that point. And we can do that for any point in that plane. So therefore, the first one is a valid description of that plane. Let's look at B here. So let's do some erasing real quick. B is the span of V2 and V3. And in this case, V2 and V3 are multiples of each other. V3 looks like it's twice V2, or at least something like that. And because of that, then we're never going to be able to get to a point, like we said, over here. Any linear combination of V2 and V3 are just going to stay on that line. So this is not the case. This is a line in R3. Let's now look at the span of V1 and V3. And for the same reasons above, for part A, this is also going to span the vector. And let's look at this special point over here. This point will be written as 2V1 plus 1/2 V3. We don't have to have just integer multiples of those vectors. We could do something else. We go over twice in the V1 direction and then half of that V3 vector. So this is a description of H. There's more than one description of H, but that works as well. And then finally, let's look at the span of V1, V2, and V3. V1 and V2 we know span that plane. V3 and V1 also span that plane. If we look at all three vectors together, that's not going to get us anything more than just that plane. I think it should be fairly clear that we at least get that plane, but we get nothing more. And again, that's because V2 and V3 are constant multiples of each other. Again, V3 is twice V2, or V2 is 1/2 V3. So because of that, this is going to span the entire plane, but there's something different about that. It's not the best way that we could write that span. And that's kind of the thing we're going to say at the bottom here. This is not the best way to write this. The best way to represent the plane H. A and C are better ways to represent that, and I wouldn't say one is better than the other. So, talking about our new idea, a basis set, or just a basis, and sometimes this is referred to as a base set. This is an efficient spanning set containing no unnecessary vectors. That's what a basis is going to be for us. And in this case, we can look at A and C. These two sets are both examples of basis sets or bases for H. Note that bases is the plural for basis. There's more than one way that you can write that. Again, we have two options here. But D is not an example of a basis because it's not efficient. And this idea of efficient is going to mean a minimal spanning set. We'll see that later on formally. So a minimal spanning set means that there's no extra vectors in there like we had for part D. So let's define a basis now. H is a subspace of vector space V. Then the index set of vectors B, B1 to BP, we use the vectors B for basis often, in V, is a basis for H, these vector space H, if B is a linearly independent set and H is equal to the span of those vectors. So we can say also, kind of putting these together, that a basis is a linearly independent spanning set. And this is how we're going to bring these two ideas together, and that a basis is the thing that is both linearly independent and a spanning set at the same time. We're going to have some other ideas to kind of think about basis. In fact, we just had one before. We talked about a minimal spanning set. We will introduce the idea that B is a maximal linearly independent set, and we'll have some other ideas later on in different sections. A lot of what we worked for in this semester, introducing linear independence, introducing span, as well as a lot of other ideas, has got us to this point that we can talk about a basis, and bases are very, very important in talking about vector spaces. Let's look at an example of a basis. This is the standard basis for R3. We call EI the standard basis vectors. We talked about that before. EI is the ith column of the identity matrix. I sub n. So in this case, we have E1, E2, and E3 are the vectors. We want to show that this is a basis for R3. And in that case, we need to show that it is linearly independent and that it spans R3. To show linear independence and span, we can think about the matrix where we have those vectors be the columns of the matrix. So we're going to look at this matrix A here, and A is going to be consisted of the columns of those standard basis vectors, and that's where we get this to be I sub 3. And again, that's because EI are the ith columns of the identity matrix. In this case, since A has 3 pivots, and we have 3 columns and 3 rows, the columns of A are linearly independent. That's from the invertible matrix theorem. We have no free variables, we have no linear dependence. And the columns of A are going to span R3, again, by that invertible matrix theorem, that all of these are equivalent. Therefore, this standard basis, E1, E2, E3, is indeed a basis for R3. We talked previously in the semester about these vectors and how they are building blocks for any vectors in R3. So let's let any vector be in R3. Let's just take -2, 4, 5 halves. This is a vector in R3. And no matter what vector you pick, you can just rewrite this as a linear combination of those vectors. This is going to be equal to -2 times that first standard basis vector plus 4 times the second plus 5 halves times the third. Now really that's just the idea of a spanning set, that I can rewrite that as a linear combination, but there's something special about having it being a minimal spanning set. This is the best way that I can do this building block kind of idea. And there's something special about E1, E2, E3. It's the easiest way to have a basis. There are many others, and we'll look at some others later, but because of that, this is called the standard basis for R3. Now let's look at a completely different vector space, in this case Pn, Pn again being the set of polynomials of degree at most n. And we're going to look at this set 1t, t squared, t cubed, all the way to t to the n power. And we're going to show that this set is a basis for Pn. That means I need to show that it is a spanning set, and I need to show that it is linearly independent. It is very clearly a spanning set because the definition of any polynomial in Pn is going to be a0 plus a1t plus a2t squared plus all the way to antn. That is an element in P sub n, and that is exactly a linear combination of those vectors in S. So it is very clearly in the span of S that it is a spanning set. To show linear independence, I need to look at the definition. I'm going to look at a linear combination of those vectors, set them equal to the 0 vector, and in that case, I need all of those constants to be 0. And in this case, that's again pretty easy because the 0 vector in this case is 0 times 1 plus 0 times t plus 0t squared all the way to 0 times t to the n. That's what's defined to be the 0 vector in these polynomial spaces. So, because it is spanning and linearly independent, S is a basis for Pn, and we call this set the standard basis for Pn. Just as we had a standard basis for Rn before, now we have a standard basis for Pn. And it is all the monomial polynomials that we have, 1t, t squared, t cubed, all the way to tn. Let's look at another example, in this case back to R3. We're going to ask, is these three vectors, does this represent a basis for R3? It is not the standard basis, but it could also be a basis for R3. So the vectors are 1, 2, 0, 0, 1, 1, 1, 0, 3. We need to show that it is spanning and that they are linearly independent. Just as we did before, let's look at the matrix. So the columns of that matrix are those vectors that I'm talking about. In this case, A is going to be 1, 0, 1, 2, 1, 0, 0, 1, 3. And if I row reduce that, doing negative 2 row 1 plus row 2 into row 2 and negative row 2 plus row 3 into row 3, I get this matrix in reduced echelon form, or sorry, row echelon form, not reduced row echelon form. And there are 3 pivots in that echelon form. So because of that, I have no free variables, which means that I am A is a linearly independent set of, or the columns are linearly independent. And therefore that they span R3, again by the invertible matrix theorem. We go back to that theorem and all those equivalent statements. So because it is spanning and linearly independent, the set of vectors is a basis for R3. All right, let's look at some non-examples and show why are these not bases for R3. First we have A, 1, 2, 3, 4, 5, 7, 0, 1, 0, 1, negative 3, 7. This is not a basis because the corresponding matrix will have a free variable. That means this is going to be linearly dependent. There are too many vectors here. So we're talking about R3. If I have 4 vectors, that's too many. We have too many columns, not enough rows. That's going to be linearly dependent. In the same way, B is not going to be a basis because there are too few vectors. This isn't going to be an issue with linear dependence, but this is not going to span R3. This is going to give a plane in R3, not the entire space. So because there's too many vectors, we have an issue with linear dependence. If there's too few vectors, we have an issue with the spanning set. And then C, even though we have the right number of vectors, this is also not a basis because 2, 4, 6 is a multiple of the first vector there, 1, 2, 3. So therefore, the span of these vectors, 1, 2, 3, 4, 5, 7, and 2, 4, 6, we could rewrite as the span of just the first 2 vectors because the other one is going to be in that span itself. And therefore, this is not going to span R3. It is a plane in R3. So just because you have the right number of vectors does not necessarily mean that we are going to have a basis. This is linearly independent, or sorry, this is a linearly dependent set as well, as we could say. This is not, I should say, this is not linearly independent. So let's look at our new vector spaces we talked about in the previous sections. That is the null space and the column space of the vector spaces, or of a matrix. To find a basis for the null space, we're going to go through a very similar process as we did in the previous section. So let's look at the same matrix as we did in the previous section, this 2 by 5 matrix, and look at if we can find a basis for this vector space. Note that the null space of A is a subspace of, in this case, R5. All right, so to do this, we're going to row reduce the augmented matrix corresponding to AX equals 0, the homogeneous equation. And if we do that, we get this matrix in row reduced echelon form. And here we have 2 pivot columns. And the rest here are free variables. Two, 4, and 5, x2, x4, x5. Those two equations we can rewrite as x1 equals negative 2x2 minus 13x4 minus 33x5, and x3 equals 6x4 plus 15x5, and again, x2, x4, and x5 are free variables. So if we look at the solution to this homogeneous equation, which is what the null space is talking about, we have our vector x here, x1 to x5. We can rewrite x1 and x3 in terms of x2, x4, and x5. And then we just rewrite x2 equals x2, x4 equals x4, x5 equals x5 because they are free variables. They can be any value that we want. There are infinitely many solutions to this homogeneous equation. And if we separate out the x2, x4, x5 and write them as vectors, we get this vector equation, x2 times the first vector we're going to call u, the second vector v, the third vector w. That's what this last equation is saying. x2u plus x4v plus x5w. So because of that, we know that u, v, and w is a spanning set for the null space, and we need it to be spanning set. Now we need to show that they're linearly independent, but we actually already did that in the last section that showed that it was linearly independent. So therefore, this set is a basis for the null space. And this wasn't just by coincidence that just these were linearly independent. We said that in this process, we are always going to get a linearly independent set. So therefore, this technique is always going to provide a basis for the null space. We need to row reduce the augmented matrix of the homogeneous system and then rewrite the solution in a vector form, and those vectors form a basis for the null space. So now we're going to look at a new theorem, the spanning set theorem. Before we get there, let's talk about a basis can be constructed from a spanning set of vectors by discarding vectors which are linear combinations of the preceding vectors in the index set. We've already referenced that idea a few times, that if you have a vector that is a linear combination of the other vectors, then that is not going to be a basis, that's not going to be linearly dependent. But now we're saying that if we remove that vector, then we will have a basis, or we can construct a basis by continuing to remove problem vectors in that form. So let's look at an example of that process. Here we have 3 vectors. v1 is negative 1, 0. v2 is 0, negative 1. v3 is negative 2, negative 3. And the important thing to understand here is that v3, which is negative 2, negative 3, is 2 times v1 plus 3 times v2. It is a linear combination of the other vectors in that set. And therefore, that means that v1, v2 is not linearly dependent. That means that this is not the best way to write the spanning set. So to show that, we're going to say let x be any vector in that spanning set. And we can show that we can rewrite it instead just in terms of v1 and v2. We're going to show that the spanning set of v1, v2, v3 is equal to the spanning set of v1, v2. We don't need that v3 vector, that this is going to be an unnecessary vector for the span. So, x is in the span of v1, v2, v3. It can be written as a linear combination of those vectors, but we can rewrite v3 itself as a linear combination of the vectors v1 and v2. So we know that v3 is 2v1 plus, there should be a 3v2 And therefore, we have that x is going to be equal to c1 plus 2c3 v1 plus c2 plus 3c3 v2. Those are more complicated constants, but they're still just constants, and therefore x is in the span of v1 and v2, showing that v3 was unnecessary, and that we can rewrite the span just with those two vectors. So putting that formally, the spanning set theorem says let S be a set of v vectors in a vector space V, and H be the span of those vectors. If one of the vectors is a linear combination of the other vectors in S, then the set formed by S by removing VK still spans H. We can get rid of the problem vector, and we still have a spanning set. The other part of this theorem says that if H is not equal to the zero vector, then some subset of S is a basis for H. That eventually you could continue to decrease the amount of vectors by looking at this linear dependence relation, and eventually get to a basis for H. That's going to terminate that process. We don't need different vectors to work with. We just need to decrease or eliminate the problem vectors. Since we looked at the null space of A, let's look at the column space of A as well. So we're going to find a basis for the column space of A, where A is going to be given by four column vectors, A1 to A4, given by the 4x4 matrix to the right there. First, let's row reduce that matrix. In that case, we have we're going to do some row reductions. We get to 1, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 4, 5, 0, 0. And in this case, we have two pivot columns. And these guys are going to correspond to free variables. And we're going to call those vectors B1 to B4. These new vectors, so B3 or B4, for instance, is the vector 4, 5, 0, 0. Where A4, for instance, is the vector 4, 3, 22, 16. It's going to be important to think about those two in different cases. So let's continue this example on the next page. I've actually rewritten what we have on the beginning here, looking at the matrix A and the matrix B. And note a couple things here. Note that B2 is 2 times B1. Again, B2 is the second column here, and that is twice the entries of B1. It's pretty easy to see in that case. But what's also true is that A2 is twice A1. If we look at the matrix A, the second column is twice the entries of the first column. It's not as easy to see, but it's true, and that follows from the fact that it's true for B. It is also true that B4 is 4B1 plus 5B3. And it's not too terrible to see in this matrix B that if I take this first column and I multiply it by 4, and I take this third column and I multiply it by 5, those look like the standard basis vectors in some way. We get to this third column, 4, 5, 0, 0. 4 times the first plus 5 times the third is going to give us that fourth vector. And it's much harder to see, but it's true in the matrix A as well, that if I take 4 times this first vector plus 5 times the third, I will get to the fourth vector. Let's try that just for one of those entries. If I take 4 times the 3, that's 12, plus 5 times the 2, that's 10, I get the 22 in that fourth vector. So it is true as well in the matrix A. Let's look at a couple other things. In the matrix A, we can see that, the matrix B, we can clearly see that B1 and B3 are not multiples of each other. And because of that, that's also going to be true for matrix A, that they are also not multiples of each other. That still holds true. And all this is just saying that elementary row operations, how we got from matrix A to matrix B, they do not affect linear dependence relations among the columns of the matrix. So because of that, if we want to decide are the columns of A linearly dependent or independent, we can instead look at the much easier question of are the columns of the row-reduced matrix B linearly dependent or independent? And in this case, if we're looking at the span of those vectors, the span of A1, A2, A3, A4 is just going to be equal to the span of A1 and A3 because of those linear dependence relation. Again, that's because A2 is equal to 2A1 and A4 is equal to 4A1 plus 5A3. Because we can write those as a linear combination of other vectors, we can delete them and we still have a spanning set. And those two vectors form a linearly independent set. Therefore, we have a basis for the column space. We know that these are going to be linearly independent, A1 and A3, because they are not multiples of each other. Again, that's what we showed above. We showed that A2 is a constant multiple of A1, therefore we can just get rid of A2, and A4 is a constant multiple of A1 and A3, or is a linear combination of A1 and A3, so we can get rid of that. And then since A1 and A3 are not multiples of each other, it is now linearly independent, and therefore forms a basis for the column space. And note that A1 and A3 were the pivot columns of the matrix A. And that's how we're going to decide the basis for the column space quickly, is that we're just going to look at what are the pivot columns of A. So again, that's that theorem right there. The pivot columns of a matrix A form a basis for the column space. So let's look at another example here. Let V1, V2, V3, given by those vectors there, find a basis for the span of those vectors. That is the column space of A, where A is equal to the columns given by those vectors. So by row reduction, this matrix A can be row reduced into this reduced echelon form. This is actually row reduced echelon form. And the pivot columns are going to be the first and third columns. So because of that, the pivot columns in A are the first and third columns. And that's what we want. We don't want the pivot columns of the reduced matrix, but the one in A. So therefore, a basis is going to be the first column, 1, 2, negative 3, and the third column, 3, 6, 9. Looking at just what the pivot columns of A, not the pivot columns of the reduced matrix, but the pivot columns of A. That is a basis for the column space of A. So reviewing this idea of bases for the null space and the column space, to find a basis for the null space of A, we're going to use elementary row operations to transform the augmented matrix of the homogeneous system, A0, to a row-reduced echelon form, B0. And we're going to use the reduced echelon form to find a parametric form of the general solution to AX equals 0. And the vectors found in that parametric form of that vector equation form a basis for the null space of A. Another way of thinking about it is the non-pivot columns, the columns associated with the free variable of B, form a basis for the null space of A. And that's not quite correct. We should say that the non-pivot columns, the free variables, that's what we mean by the non-pivot columns, of B determine, that they don't form a basis, but they determine the vectors in a basis for null space of A. So you don't want to say that the actual free variable vectors form the basis, but they determine the basis for null space of A. And for the column space, a basis for the column space is formed from the pivot columns of A. And again, big warning here, use the pivot columns of A, not the pivot columns of B, the reduced row echelon form of A. We can find what the pivot columns are with B, but we have to use the original column vectors there. In the next section, we're going to continue talking about bases, and we're going to talk about the idea of dimension, how many vectors are in a basis.